This is our linear motion unit all the way up until velocity. What this is going to cover is relative motion. It's going to cover distances, displacements, is going to cover speed. The formula for speed is going to cover velocity. Also the difference between vectors and scalars. So the objective on last Friday was to calculate speed of object using distance divided by time. And we had done an activity outside where we measured our speed. So how would we know that an object would actually be moving? Well, our object is always going to be moving if its position changes. And the position is relative to a fixed point. When we worked in the workbook, we had that example where there was a cinema, a post office, and we always had like an origin point, no matter where you were walking to. That's what we need in physics. We need to have a frame of reference, and that is almost always the surface of the earth, unless otherwise stated. Motion is something that's relative. So that means that even things that appear to be at rest can be moving. So for example, you could have a book on the table and it's totally still, right? You say it's not moving, but that's relative to the surface of the earth. What if you were relative to the sun? Well, our own earth travels 30 kilometers per second around the sun. So relative to the sun, that book that is at rest is moving 30,000 meter sticks long for every second relative to the sun. And then even faster than that is if we took our own solar system, how that moves around the Milky Way galaxy. So we always want to have a reference point. Motion is relative. Look at the road here. The cars are racing in the Indy 500 and they move relative to the track. We learned about distance and displacement. Let's say one lap around the Indy 500 gives you a certain distance. But if you're looking at displacement and your starting point and finishing point were at the same line, you would have said that there would be zero displacement. So displacement is concerned with direction and position, but distance is only considered with measuring length. So when we discuss the motion of something, we're going to always describe it relative to something else. This is called our frame of reference. It's always going to be the surface of the earth unless we state otherwise. So if we talk about a rocket ship going up, that's relative to the earth. If we're talking about a submarine going down, that's relative to the surface of the earth as well. Same for cars on the street. So we're always going to be looking at the surface of the earth for our frame of reference. You can calculate the speed of the object by using the formula of distance divided by time. Now, before Galileo and the scientific revolution, people described things qualitatively, slow or fast. You'd say that the tortoise was slow. You would say that the hare is fast. And these descriptions were great, but they didn't have any numbers to them. They're too vague. They're not quantified. So Galileo is measuring speed. He's quantifying it. And speed is a measurement of how fast an object is moving. So if you missed it, here's our formula for speed. It is our distance divided by time. Here's some example units. You can have miles per hour, kilometers per hour, centimeters per day. You can have light years per century. Now our SI units for speed are going to be meters per second. Speed is a scalar. It only depends on a magnitude or a quantity. Speed does not care about direction. More on that later. Okay, we had done a worksheet. Let's talk about units. We're primarily using the SI units of meters per second when we talk about speed. For example, the cheetah can run 50 meters every 2 seconds. So its speed would be 50 divided by 2. 50 meters over 2 seconds. That gives us 25, the unit meters over seconds. So the units stay in our division problem there. For example, you can compare some common speeds here. If you're bowling and you are bowling 12 miles per hour, in meters per second, that's about 6 meters per second. What about somebody who hits a baseball? 100-mile-an-hour baseball in meters per second is about 44 meters per second. In places like Canada and the UK, they use kilometers per hour more commonly. I don't know quite why we've never made the switch, but in our science class, we're going to try to stick to the SI units whenever possible. Now, there's two differences that we're going to talk about with speed. One of them is instantaneous, and the other one is average. So if I'm in my car, it doesn't always move at the same speed. Sometimes I make a left, slow down, make a right. I come to a stop sign. There's a green light. I go. You can tell the speed of the car at any instant only by looking at its car speedometer, right? The speed at any speed is called instantaneous speed. We could do this in our class by drawing the tangent of a line when we're graphing speed, but we're just going to call it the speed that you can find when you look at the speedometer. The speed that we're going to calculate in class is going to be average speeds. So what type of speed does the speedometer tell us? Instantaneous speed. And you can see that miles per hour or kilometers per hour on this one as well. The average speed that we calculate, for example, in our trip in our car, it's not going to travel the same speed the entire trip. The driver cares about the average speed for the trip as a whole. For example, when you're mapping it out or you're using your GPS, it's telling you an average speed. It's not taking into account every single stop that you take and slow down and speed up that you take, because they're kind of calculating where you're at and your trip so far to tell you what your average speed could be. So the average speed is the total distance divided by the time. Let's do a calculated example of average speed. Let's say you went 240 kilometers during a time of 4 hours. You had an average speed of 240 divided by 4. It would give you 60 kilometers per hour. So we would take our formula for average speed, total distance covered divided by the time that passed. And you're simply plugging and chugging away. So what we like to do in our physics class is when we get a word problem like this, we take a guess. We take our givens, we take our unknown, we look for the equation, and we substitute and solve. Given, unknown, equation, substitute, and solve. So in this case, the given was 240 kilometers and 4 hours. The unknown would be what your average speed would be. Your equation would be right here, average speed. Substituting in the values, you get to solve for 60 kilometers per hour. So we'll use those type of strategies throughout physics. Given, unknown, equation, substitute, solve. All right, let's take a quick look at velocity. I'm going to pause this recording because my slide is not in white. Okay, I figured out the problem. I need to hit the animation. So speed is a description of how fast an object moves, while velocity is how fast and in what direction an object moves. So in English, we always use these terms interchangeably. In physics, we have to be very specific. Speed does not care about direction, velocity does. So speed is a scalar, velocity is a vector. So in physics, velocity is speed in a given direction. So when we say a car travels 60 kilometers per hour, we're actually telling you the speed. But if we said the car was moving 60 kilometers per hour to the north, we are specifying its velocity. Velocity is directed speed. Velocity is speed with a direction. So quantity such as velocity has a direction as well as a magnitude. Oh yeah, it's called a vector quantity. Speed, however, is a scalar. Velocity, just like force or acceleration, is a vector. Velocity is a vector. Let's look at the difference between, say, constant velocity and changing velocity. Constant means it stays the same, right? So constant speed would mean a steady speed. Something with a constant speed, it doesn't slow up or doesn't slow down. If you're on a roller coaster and it's jittery, that's not constant speed. Constant speed would be smooth the entire way. Constant velocity goes one step further. Constant velocity means you have to have constant speed and constant direction. So you have to be going the same speed and you can't turn. So constant direction would be a straight line. So constant velocity means motion in a straight line at constant speed. Motion in a straight line at a constant speed is constant velocity. What if we had changing velocity? Well, if either the speed or the direction or even both are changing, then the velocity is changing, like this car going around the turn. So constant speed or constant velocity, they are not the same. A body, or say this car, might move at a constant speed along a curved path, but it does not move with constant velocity. That's because the direction was always changing. You're not going in a straight line when you're going in a curve, right? So think of a car on a circular track. The car might have a constant speed, could be going the same speed, but not a constant velocity because the direction of motion is changing. It's always changing. At every instant, the car is changing direction. Let's sum up speed versus velocity, basically scalar versus vector. Let's start with speed. Speed is a scalar. The SI units are going to be meters per second. And our formula is distance divided by time. If you want to find time, you can take distance divided by speed. And if you want to find distance, you can take speed times time. Velocity is similar in the fact that it has the same units, but velocity is a vector. My SI units are also meters per second. My formula is very, very similar. Velocity is going to be, instead of distance, displacement, because displacement deals with changing position. So displacement divided by time gives you velocity. Time is the same as displacement divided by velocity, and displacement is equal to velocity times time. That should do it for today.